Hi everyone. Let's start a new unit, unit number 9. The general topic for unit 9 is enolate chemistry. And the first reaction we're going to look at in this unit is called the Aldol reaction. Before we look at the reaction, we do have to explain what an enolate is, and their pKa's are going to be very important for our understanding. Now, before we get to the notes, the illustration shows that these types of reactions can occur or do occur in our body. And this is a human aldolase and an enzyme. It's an enzyme that can catalyze the aldol reaction in actually both directions. In the direction I'm showing, it looks like it's making a monosaccharide. So this enzyme can break down monosaccharides or build up monosaccharides, and which is very interesting. And this is a reaction that you're going to become very familiar with, an aldol reaction. Okay, before we get to the actual reaction, I do have to go over what an enolate and look at their pKa's. Now, enolate might look very familiar to you. It comes from the term enol. Let us review enol keto tautomerization or keto-enol tautomerization. An enol is an alcohol that has an alkene. So that's a good representation of an enol. And we'll call this the enol form, because in solution, that form can toggle between the enol form and the keto form. So this is not resonance. This is actually an equilibrium. And for the most part, the keto form is the more prevalent of the two, keto form. What is an enolate then? An enolate, the ATE, if you remember from carbohydrates and your carboxylic acids, that represents the anion form of the enol. So we have an enolate that looks like this, O minus. Okay, and now we do have resonance. See, we don't have resonance up here because atoms are moving. Atoms don't move during resonance, only electrons. But here, electrons are just moving. And there are two forms in the enolate that we should be familiar with. The two forms are the enol form and the keto form. But now we have an anion right here. That's resonance. Most people think of the enolate as actually this molecule here, but both of them are considered the enolate. They actually both represent the same enolate because you know that resonance structures aren't real. The actual molecule looks like a combination of the two in what's called the resonance hybrid. So when a professor says enolate, you got to be prepared because either one of these is correct, okay? And you would probably want to know both. Because what do we have here now? We have an anion. So we have an attacker. We have nucleophiles. We could have an O nucleophile if the form attacks in this, well, if this form attacks from the O minus, or we could have a C nucleophile. We'll get to, when we look at the aldol, what do we have to draw? Which resonance form is preferred? And where does the attachment take place? Does it take place at the oxygen, or does it take place at the carbon? Okay, but that will come in due time. Let me talk about the pKa's, okay, which we were planning to do anyway. Let's see. Let's find an acidic proton. Let's compare it to a proton that's not acidic. So the proton I'm putting in a square, that's an alkane, and that has a pKa very, very high, around 55 to 60. On my pKa table, I usually have it as 60. But by adding a carbonyl group, and I will use, let's use this example. By adding a carbonyl group, we lower that to what? We lower that to around 20. That's a little bit surprising. Okay, that dropped by 40 pKa units. And that's because when we deprotonate at this position, it's resonance stabilized, the anion. And that's why it's okay, or relatively okay, to remove this hydrogen versus this one over here. This hydrogen is called the alpha hydrogen, okay? And we've seen that before in the carboxylic acid chapter, alpha, beta, gamma, delta. Alpha, beta, gamma, delta. Yep, that's the order. So that drops. So we'll be able to make the enolate, and again, I'm going to show you my preference, which one you want to draw, because both are valid, but I believe one is better than the other. And we're going to start doing reactions at the what? At the alpha carbon. And that is the key point about this enolate unit. We are doing reactions at the alpha carbon. Very interesting reactions. Let me give you another couple pKa's. How about if this was an aldehyde? Does that change things? It does change things quite a bit because we don't have an electron donating group on the left side of the molecule. Can you predict whether this pKa is going to be higher or lower? More acidic or less acidic? We don't have an electron donating group, right? Alkyls are electron donating, and that's not great because if you're donating electrons, then you're making that charge more negative, right? You're pushing electrons into this carbon. The fact that we don't have an electron donating group on the left side makes this even more acidic. And I'm going to say 17. The pKa values that I'm getting these from, the source I'm getting these from, are from Evans' pKa table. Okay. If you want to Google that. Now, what do we know? What other molecules do we know have a carbon-oxygen double bond? Esters. And this will be another example. Again, you can test your intuition and ask yourself, is the pKa of that hydrogen going to be higher or lower? Let me just label these aldehyde. And this is an ester, as you remember from your carboxylic acid derivatives. And this is a ketone. Can we do alpha carbon chemistry for an ester? Yeah, but let's see. This oxygen is electronegative, but also it's electron donating due to resonance. It turns out that this is less acidic. The pKa is around 24. Okay. Let me jot down a couple more, and then we're just going to jump into the aldol reaction. A couple more are these. Look at this alpha carbon in the middle. This is a dialdehyde. The aldehyde has a fairly low pKa, but now we have an opportunity. Imagine there's a negative charge here. The negative charge can be distributed to the left and to the right, both sides. Over here, it could only be distributed to the left to make the resonance. So this is doubly stable. It has two, when you have the anion, you have two ways to move that anion. Bottom line is this has a very low pKa, pKa around 6. Man, that's almost like a carboxylic acid. Carboxylic acid have a pKa of 5. That's remarkable because that proton is on a carbon. Normally that is not very acidic. Now, if we have a diketone, okay, ketones are a little bit less acidic, but here we have it as a diketone. A monoketone, or just a ketone, would be 20. The diketone now becomes 9. Again, you can have resonance, and you could practice with this. Let's say I deprotonate the alpha carbon. Okay. What are your resonance structures? What is your first resonance structure? Technically the second, right? And then can you take that resonance structure and perform resonance again and get a third resonance structure? Okay. Go from A to B to C using your mechanism arrows. Structure A to structure B to structure C. What are we missing? We're missing the diester. The diester, the monoester is the highest pKa out of these three. Look at the diester. Oh man, I'm going to draw it upside down now. There's your diester. Again, you still have an alpha carbon. You're going to want to identify your alpha carbon for these reactions, and the pK is 13. All of these are more acidic than an alcohol, which is still remarkable, because when you deprotonate an alcohol, you get that minus charge on an oxygen, which is more electronegative than a carbon. But due to resonance, these are more acidic than your alcohols, most alcohols. Okay. All right, there's your pKa's. We have 6 of them. Before I go to the aldol reaction, because we're trying to have reactions at the alpha carbon, it is essential that we deprotonate the alpha carbon. Therefore, these pKa's are going to be important in us deciding what kind of base we want to use. And in the Aldol reaction, we're going to use an unusual base, sodium hydroxide. I know that sodium hydroxide is not unusual. What's unusual about sodium hydroxide is that it is not strong enough. It's not strong enough to fully deprotonate the alpha carbon. But there's a reason why we want to do that. We'll go through this slowly. Reaction 9A. Aldol reaction. Rxn. The Aldol reaction we're going to learn right now is a reaction between two of the same types of molecules. Let's take an aldehyde. Let's take this aldehyde here, propanal, and I said that we were going to use sodium hydroxide. We could use other types of oxide bases, and I'll show you some examples, but let's use sodium hydroxide and visualize. That OH minus is going to rip off some of these alpha hydrogens, or the alpha hydrogen on some of the molecules. Not all the molecules. We're not going to get 100% deprotonation. And then, this is the interesting part, think about that anion. That anion is going to attack another one of itself, but the one that's not deprotonated. So again, green is going to be sort of like scratch work, because eventually you'll have an anion, and that anion is going to attack this carbonyl. Very interesting. The same molecule can act like the nucleophile or the electrophile. Let me draw you the final product, and then we'll go through the mechanism. I think the mechanism will clear up a couple things. Now, the final product, I have a technique. The technique is you draw your attacker as is, but I'm going to draw my attacker flipped. And I'm going to move this carbon out of the way, the alpha carbon. Okay? Because that carbon is going to attack, and I like attacking to the upper right. Therefore, I'm going to make a bond like this. If you've seen my videos before, you know that I like to put a dot on the carbon that's being attacked, and it's that dot right there. Maybe I should have made this green. When you attack this dot, you get an O- that will eventually be protonated. So why don't I put sodium hydroxide in water? I should have put that originally. But what is attached to the dot? We have 2 carbons and a hydrogen that you do not have to draw if you don't want to. But I'll draw it anyway, like this. It seems complicated at first. I'm going to try to give you clues or tricks how to get to the product without having to draw the mechanism formally. But for now, what you want to visualize again is draw your attacker as is, but get it situated so you could attack to the upper right, to the northeast. You could attack that dot. Again, this is scratch paper. I'm just drawing this again to visualize the attack. And then the carbonyl group becomes a hydroxyl, and then make sure you add everything else connected to that dot. Mechanism. The mechanism starts out with deprotonation. I did say we're using sodium hydroxide. Let's see if we could decipher why we want to use sodium hydroxide. We have OH minus. Yeah, this is good. We grab this hydrogen, proton. Oh, now this is a preference of the professor because I'm going to deprotonate this carbon. Do I want to deprotonate it so it looks like this form, the carbon anion, or do I want to deprotonate it so it looks like this, the oxygen anion? For a lot of professors, it doesn't matter. Okay. For me, I would prefer that you draw this form. Now, why would that be the case? Because, well, first of all, in terms of resonance, this is the major contributor because the negative charge is on the more electronegative atom. So if I'm drawing the enolate, maybe I could estimate that this is 80% contributing and this is 20%. Okay. Again, the molecule is a combination of these two, but they don't have to contribute equally. It could have a little more charge on the oxygen than it does on the carbon. Think about that. So I do want to draw the oxygen anion. So instead of making the anion onto the carbon, this is very important, shift that bond to the bond next door, and then shift these electrons up to the oxygen. Would I take off points if a student draws the carbon anion? No, I wouldn't. But this is how I teach this reaction. I want to make the oxygen anion. Now, you don't have to draw this hydrogen down here if you don't want, but I'll do it. Just to emphasize that we removed one of the protons. Plus H2O. Okay. Alright, so in the mechanism, on an exam, you're drawing what's blue and what's green. In pink, let me give you a couple notes because this is what's interesting. The pK of this, we said, was around 20. No, of an aldehyde, around 17. Ooh, very close actually. The pK of water is 15. Equilibrium favors the weaker acid. So this is the weaker acid. We're not making 100% of the enolate. Let me write that down also. Enolate. Is that good? Look at what I have here. The electrophile should still be neutral. I don't want to deprotonate 100% of my starter material. I want some percentage so I can attack it. I need some of this. Now, once this attacks, okay, we're losing the anion to make the product. We're going to reestablish equilibrium, and we're going to get some more of the anion, and it will just keep siphoning from the starter material to make more anion until everything is reacted. But again, the point is, I want some of this to be neutral. I want some of this to stay neutral so I can attack it. So I don't want 100% of the enolate. What I do want is, and it's kind of crowded, I'm going to draw the other partner, okay, right, the aldehyde. And how do I attack this dot carbon here? Now I want to attack through the carbon. Okay, again, it gets a little bit tricky because it does seem like I'm toggling back and forth between the two different forms of the enolate. In the mechanism, the first enolate I see, I want the O- because that is the major contributor. But when I make the bond to that dot, okay, make sure you push up now this pi bond up to the oxygen. I want to attach that dot to the carbon, not to the oxygen. I want to attach that dot to which carbon? The alpha carbon. Again, this is the alpha carbon. A little bit crowded. Can you draw the result? Now you could either draw it like this, okay, or you could draw it the way the carbons are situated. Let me draw it the way the carbons are situated, actually. Do you see how I remade that aldehyde, this top piece right here, by putting back the double bond? And now let me move this hydrogen a little bit out of the way, this one right here, because I am making a bond to the dot. What's on the dot? The dot has a couple things. It has a hydrogen, it has a alpha group, and now the carbonyl group becomes an O minus. O minus. Okay, we're not quite done yet. We have to protonate. Am I getting close to the expected product? You'll have to be the judge of that. Okay, use color pens at first, but let's see if we do get the final product. We're just going to protonate with water to recreate sodium hydroxide, actually. And here we have this attack, and we have this. Okay, maybe it'll be easier if I don't draw these hydrogens. Okay, and then we can see a little more clearly where the points of attachment are. Dot OH. We have to convince ourselves or verify that this is the product we wanted. Let me give you another clue. In an aldol reaction, look where the hydroxyl group ends up being. It ends up being on the beta carbon. So this alpha carbon always stays alpha. That's the alpha, and this is the alpha. It's the carbon next to the carbonyl group. You know that you did an aldol reaction correctly if you formed what's called a beta hydroxy aldehyde or ketone. Or you could say beta, sorry, there should not be an L here. Don't do that. And I'm wondering if I should put a space. Beta hydroxy carbonyl, put a space. This happens to be a beta hydroxy aldehyde. Okay. This product is called the aldol product. And it's a very interesting reaction. You could make it a little more challenging by doing different aldehydes. You could even use a ketone, and maybe that will be my next example. But it's also interesting because, again, these reactions will take place or do take place in your body. Not only aldols, but if we look at the full title of the unit, Clazins, which we'll get to in a couple of videos, and the Michael addition. Those reactions take place in your body and in different organisms. So remember, in an aldol reaction, you're making the beta hydroxy carbonyl, beta hydroxy aldehyde, or beta hydroxy ketone. You could always double check that. Let's double check that. This is our mechanism right there, and we were able to get this product. Also, we created an hydroxide molecule. Okay. But let's verify this. Here's your alpha, here's your beta. We did make a beta hydroxy aldehyde. What else can we verify? This molecule has 3 carbons. It's a C3 molecule. But I added it to another one of itself. There should be 6 carbons here. 1, 2, 3, 4, 5, 6. C6. Okay. What you want to get good at, after practicing the mechanism a couple times, is you want to get good at getting the product without having to go through the mechanism by using the tricks that I'm showing you. How about this trick? Or not this trick, but this reaction. Let us make it a ketone. And give me 1 second. Do I want to make it No, I don't want to make it asymmetrical because I'm going to get a mess because I could form the enolate to the left or to the right. So we should make it symmetrical, where it doesn't matter whether I deprotonate on the left or the right. We could use the base NaOET, sodium ethoxide. Just remember that you need a proton source, right? Here we had water. Typically, the proton source, you want to match the salt because the salt will be more soluble in the same looking solvent. So this is sodium ethoxide. Maybe we should use ethanol, ETOH. Okay, that will provide the proton. Okay, so listen to my tricks or tips, and you're going to rewind this and try this again without seeing the answers. Okay. Mark your alpha carbon. You're going to pretend that that is your attacker, and if you want, I normally don't, but I'll draw the negative charge there. Again, on the mechanism, do you notice that we never had a negative charge on the carbon because I bypassed that to make the negative charge on the oxygen. But in terms of getting the final product, we're going to attach towards the carbon, and that's why I draw the negative charge here. Again, my grader's not checking my scratch work. My grader's checking what's here. The idea is to draw, and this is the hard part, I think. Draw the attacker, in this case the ketone, in such a way that the alpha carbon can attack to the northeast. That's my preference. Now, if you draw your final product like this, that's perfectly fine. Okay, the grader should be able to decipher whether this is the same as that. I like this form because you see immediately the beta hydroxy group and the carbonyl. Okay, you're going to attack a dot if you want. But again, when you're doing a fill in the product, you want to save some time. You don't want to have to fill out the whole mechanism just to get to the final product, if that's what the professor wants. The carbonyl becomes an OH, and just copy what's on the dot. You could even do this if you need to. Okay, draw like a pseudo mechanism, a partial mechanism. What's on that dot are two, on the dot are two propyl groups. 1, 2, 3, 1, 2, 3. This is also called an aldol, even though it's not an aldehyde. I don't know if you realize this, but isn't this cool why they call this an aldol? Aldehyde alcohol. Aldol. But the thing is, this process could be done with ketones as well, and they just decided to keep the name also as aldol, even though you don't have an aldehyde, you have a ketone. But the rules still follow. You still have a beta carbon here, alpha beta. It's a beta hydroxy ketone. Space. Ketone. That's the final product. At home, draw mechanism. Probably I'll ask on the problem set for this video, I'll ask the students to draw the mechanism. Okay. That's the aldol. Do this very, very well. Learn this very, very well, because the reactions that are coming forward are going to be very similar to the aldol. They're actually variations of the aldol.